All right, so today, this video, I'll be going over the lab technique PAGE, which is polyacrylamide gel electrophoresis. I'll be assuming you've already watched the agarose gel electrophoresis video, because that goes over a lot of the basics of what electrophoresis is. But I'll do a quick recap as well, just so things are a bit clearer. So first, as always, we'll start with the motivation. Let's say we have a protein, right? Let's say we have this protein. All right, I'll draw it like this, right? And it's a drug, right? And it does something in the body that we really want. Let's say it's, yeah, I don't know. Let's say it's a very useful drug, but we need to make sure it's big enough, else it might get filtered out in the kidneys, right? Proteins that are too small can get filtered out in the kidneys pretty easily. So we kind of want this protein to be big enough to where it's going to stay in the body for a bit longer so it actually does its job. In other words, we need to determine the size of this protein. Let's say, I don't know on the top of my head how big proteins have to be to not get filtered out. Let's say it's like 100 amino acids, right? And if we know this protein is bigger than 100 amino acids, then we know for sure it's not going to be filtered out with the kidney. So how can we figure this out then? Well, we would need a way to figure out its size. And if we think back to agarose gel electrophoresis, we could figure out the size of DNA by taking advantage of the negative charge on DNA, right? So I feel like it's clearly it must be something that we can do with proteins too, right? I mean, the challenging thing with proteins is that if we imagine an amino acid structure, right? Let's take our amino acid. We have our was like a carboxylic acid here, right? And then here we have our amide group. Nothing about this is really that negatively charged. Like this R group can be negatively charged, right? But I mean, it doesn't like that. That's not very consistent. So we need a better way to be able to figure this out, and thankfully we do. So that's where PAGE comes in. So what exactly is PAGE? Well, it's a method that utilizes a negative charge on amino acids. Now, there's a couple of different types of PAGE, but all of them utilize something called charge density. And what that basically means, if we have any protein, we have a certain amount of charge for that protein. Now, I think the way they calculate this is they take whatever charge it is. Let's say it's like whatever, like plus 3q, right? And you divide it by the mass, and then that's your charge density. And different proteins have different charge densities, obviously, depending on what amino acids there are, right? So there's a lot of ways. If you think about it, there's a lot of ways we can actually use this, because if we know the charge densities of each protein, right, and we know we can use actually electric current to estimate the relative size, right? If you think about that, if you have two proteins, one has, let's say they have the same charge density, and one moves a lot further, right? Chances are that one's a lot smaller than the other one, right? Now the tough part is obviously balancing out charge densities, and I'll go over how to do that. And finally, we have a protein ladder, just like a DNA ladder. We can have proteins of set sizes that we know, and set charge densities that we know, and so we can see, based on how far they go, like relative sizes, right? So that's sort of what we're going for. And also, before we move on, polyacrylamide gel electrophoresis. What is acrylamide? Well, acrylamide, it's a type of polymer that will polymerize into these like very thin, like very cross-linked. That's the word, cross-linked, like almost like a sieve. And this will actually be very good for proteins because it's very uniform, right? And we'll go over different applications of this. First, with the different types of PAGE. So there's a normal protein, right, where we just have just a straight protein. So that we can have this protein, right? It might have secondary structures. There might be like a alpha helix here, beta sheet over here, right? Maybe it has a disulfide bond here. We just leave it like that. And that we call native PAGE. You might have heard this before. Literally just means you don't edit the protein really at all, and you follow the procedure normally. And I'll go over the procedure later on, but just know native PAGE didn't do anything to the protein. Now, if we want to remove some folding, because think about it, the folding, let's say trying to go through the sieve, right? The folding will make it a bit more challenging compared to just like a straight strand, right? The protein folding makes it a bit more challenging to predict how it would move. It could skew, it can skew a lot of things. And also the charge densities on this guy, who knows, right? Maybe this guy has a lot of negative R groups, right, or has none. So there's a lot of like variations in terms of how negatively charged this protein be. So we should have ways of being able to neutralize that, and luckily we do. That's where SDS-PAGE comes in. SDS, or sodium docethyl sulfate. It looks like this. We have like a sulfate over there and a long tail, and this is just a hydrocarbon tail. And what this does is, imagine we have our protein. Let's do like this, right? So it's amino acid chain, right? What this guy will do, it'll actually denature this protein and remove its folding and bind. Let's take one. It'll be like that. Okay. All right. I'll draw the. Actually, no. I'll draw it like that. That's one SDS, and then another SDS, and another SDS. And think about how heavy SDS actually is. This is a lot of carbons and hydrogens. This oxygen and sulfate are also very heavy, right? So this will actually neutralize the charge density of this molecule, because one SDS can bind to 2 amino acids, right? So that's very consistent. But also these guys are really heavy, and each one has a negative charge, right? So with big enough proteins, especially big proteins, this actually neutralizes the charge densities and everything to where the only thing that matters is actually the length of the amino acid, and that's really key. And we can even use a reducing agent like beta mercaptophenol and mercaptophenol, and that basically destroys these disulfide bonds, right? That could be there, and that destroys all folding, right? And so what you're left with is a bunch of long amino acid strands, or I guess polypeptides, that have varying lengths but equal charge densities, or equal enough for you to accurately determine. So obviously from this, reducing SDS-PAGE is usually most commonly used. SDS-PAGE without the reducing agent is also commonly used. In native PAGE, I mean, it's tougher, but this still has its uses every now and then. So let's actually go into the buffers of this lab technique. So first we have 2 gels, right? Imagine we have the wells, right? Where we're gonna put in our protein, and in that protein we also have that protein vial. We also have a buffer. And what does that buffer contain? Well, it's tris HCl, right? Tris forms an ion, tris plus, and that's it gives a lot of ionic strength, right? And we'll see this in the running buffer too, right? The running buffer also has tris for ionic strength. But the Cl minus, the chloride ions, are what's important for this loading gel, and we'll see why later on. Obviously, we'll add our SDS and or reducing agent if we want to do SDS-PAGE. Remember, native PAGE, we don't add any of this. SDS-PAGE, we would put an SDS, and if we're doing reducing SDS-PAGE, we do SDS as well as a reducing agent. A common one is beta mercaptophenol. I hate pronouncing that word. And then we also have glycerol to add some density, right, to the buffer. And we also have to add a tracking dye. And a common one is bromophenol blue. And that one just basically like dyes the protein blue so we can see it as it moves, right? Or at least when it settles. And then the running buffer, we have tris HCl, right? So this will provide tris plus as the ionic strength, but also glycine. And glycine is very important. And I'll explain a bit more why later. Now I want to take a look at the gel as well. This gel differs from agarose gel because it's a lot more complicated. First, we need to set up like 2 glass panes, right? All right, imagine like 2 glass panes, right? This is 1 glass pane, and then 2 glass panes, right? And then we have like some walls there. You can't expose acrylamide to oxygen, so you have to keep in this glass pane. What you add first is a resolving gel solution, and you have very high concentration of acrylamide. So what you end up getting is the sieve is like very, very, like, all these holes are very small. All right, that's a key point. And we also set it to a pH of 8.8. So you add base or like HCl to make the pH 8.8. That's very key. And then you pour that in, gets like about there, right? Or maybe a bit higher. And then what you do next is you add the stacking gel. Now this is the exact same thing, except you have a lower concentration of acrylamide, right? So if you imagine you have a bigger sieve now, right? A lot of things can go through very fast. We'll see why this is the case later. And then we also set this to a pH of 6.8 using HCl and base titration, right? And then you pour that in, right? You add in your little well mold. So if I imagine the well mold, right, just like that, and you let it solidify. Great. And then that's our gel. So basically what we have, and we call this the top a stacking gel, and the bottom a resolving gel. Now, why do we have two different gels? What's the significance? Like, it seems like, well, why so complicated, right? Well, here we go. Let's draw a glycine molecule. So we have this thing over here, or I guess it starts like that, right? And then this is our glycine, CO2H, right? What happens at low pHs? So at a low pH, carboxylic acid is a very strong acid. So you need a very low pH for this H to not get dissociated. But when does it get dissociated? Well, it gets to dissociate at about a pH of, I think it's like 5.97 or something like that. And basically what you have is you get this Zwitter ion. That's what we call it. Just now the H goes, and boom, we have a neutrally charged molecule. Okay? Let me just move this side here. But then when you go above that, and you go to high pH, right? This hydrogen on this amide, right, dissociates because amide is not as strong acid. It's a pretty weak acid, but it is still an acid nonetheless, to where now it loses it, and now this molecule, this glycine molecule, has a negative net charge. Now hold up. pH 5.97. pH 6.8. Pretty similar. pH 8.8. Very high. So what do you think happens after it goes past the stacking? Like, because we have glycine, right? If we imagine in our buffer, right, our loading, our running buffer has glycine. So when we actually run this, right, with our electrode here, right, we have our positive anode here, our negative cathode up there. The glycine in the stacking gel is actually going to be more neutral. Not obviously not fully neutral because the pH is still much higher than 5.97, but not that much higher. So they'll be relatively neutral, especially compared to when it enters the resolving gel, because that's when we go to very high pH, and now we get a lot of this like dissociation of the amide acid, and now we get a net negative charge, and those glycines are zooming, right? They're going. They're very small, right? They're going to go through the little acrylamide sieves very fast. Now, why is this important? This seems like we're just overcomplicating things, right? Like, why? Well, okay, I had this slide here, yeah. So yeah, like I said, it's more neutral near the isoelectric point. But the reason why we have this in the stacking gel is because if we look at our wells, right? We have our wells here, and we put our protein in, right? This could be up to 1 centimeter. So some proteins will exit into the gel a lot sooner than a protein up here, for example, and that will smudge our results. So what we have come up with, I say we as if like I contributed, some smart people decided we should have a stacking gel. And how does stacking gel work? There's a lot of electrophysics behind it that personally I don't actually understand nearly as well, but I'll give the rough review. Here's this stacking gel, right? And this is resolving. So this is resolving gel, stacking. All right, so what happens? When we run the current, the chloride ions go zooming, right? Chloride ions are very, very small. So chloride ions, Cl minus, they're going. All right, let's imagine they're going really fast. So they're leading. We call these the leading anion, right? At the back, because the glycine is more neutral, right? Remember we saw here, we saw the equilibrium. This is at its isoelectric point, right, where it's neutral. Obviously not directly at the isoelectric point because it still needs a bit of negative charge to actually move, but it's pretty neutral, at least much closer than in the resolving gel. So we have our glycine, our neutral glycine, trailing behind these chloride ions. And now for physics reasons that I'm not super familiar with, I have a general sense with maintaining voltages, and then there's more like, I don't even know how to explain it. But either way, the net result of this is that it compresses the proteins within this little thin, narrow band. And this is very key, because what was once a 1 centimeter gap might only be like a millimeter, right? It's very, very narrow, very narrow. And then think about, as soon as this guy enters the resolving gel, right? Chloride ions are going, right? They're zooming. As soon as it enters the resolving gel, right? The glycine stops like being neutral, right? Because now it's 8.8, so now it's very negative. All the hydrogens have been, deprotonated, right? So the glycines are now negative charge, and they zoom past the proteins, and now these proteins are, nothing's anchoring them anymore, right? Now they're free, and now they're free to go as if they were just normal. So now they're all starting at the same place relatively, and then now we can actually see very thick bands, right? After we run the gel for a certain amount of time, and the gel running is the same process as agarose gel electrophoresis. So that's the genius behind the stacking gel, and it might seem at first like, well, why are we doing so much extra work? Well, this is very important. And if we also think about it, remember the stacking gel has lower concentration of acrylamide, so we have much bigger sieves compared to like the narrow sieves down here, right? And so none of the proteins are actually getting particularly slowed down. All of the proteins are like they can all fall through. Whereas here, it's definitely a lot more selective, right? And that's when we actually see differences in protein sizes. And what we're basically doing is counting residues, right? So let's take a look at some results. Look at this. So they definitely use bromophenol blue here. And we can see they track this protein. I don't know what this protein is, but you can see that we have a protein ladder over here, and we have our sizes here, right, in kilodaltons, right? These sizes are from the protein ladder. These are proteins of known sizes, and I'm not too familiar with kilodaltons in terms of like how big they are in terms of how many amino acids, but I imagine 1 kilodalton is a lot of amino acids. But we can see that this protein is exactly around 20, right? Or maybe like just over 20. And notice how narrow this band is. That's because of the stacking gel. And now we can actually determine sizes of proteins very, very well. So that's the beauty of PAGE. And just for a quick review, native PAGE, remember, we didn't touch the protein at all. We keep it in its native form. We don't do anything, but that's not great because charge densities can vary. There's a lot of folding, right? That's why we'd like to use SDS-PAGE, remember, where we add SDS, sodium doconyl sulfate. And that will basically just neutralize all of the variance in charge densities, right? Because SDS is already a pretty heavy molecule, but it also has a net negative charge. So a lot of them going on to the proteins, right? Remember, each one goes on to 2 amino acids, give or take. That will make all the charge densities of the proteins relatively similar. But also distinguish them in terms of size, right? The ones with more net charge will be bigger because there's more SDS. And the ones smaller will have less mass, but also less charge. So their mass density is the same, but their size still matters in the polyacrylamide gel. And reducing SDS-PAGE, we can use a reducing agent like beta-marcaptoethanol to get rid of the disulfide bonds that might still remain. Sometimes we might not want that, right? We might still want to see different domains interact and see if those domains even exist, for example, right? This is a good way to see, like, if we, before adding the reducing agent versus after, right? Is there a difference in how the protein behaves? That can give us hints as to whether or not there's like multiple domains, protein domains, and whatnot, right? So these are a bunch of ways that scientists can figure out, okay, how big are these proteins? What properties do they exhibit? Stuff like that. Very powerful technique. Hopefully this all made sense. Try to make it as simple as possible. Because a lot of the processes in PAGE are a little confusing, especially the stacking gel focusing, right? But hopefully it made sense. I'm going to go over isoelectric focusing in the next video. And that's also like a branch of PAGE, so hopefully that'll follow nicely. But yeah, that's about it.